joining us. So the first thing I want to mention is a quick reminder. So homework 4 over these matrix computations, that is due on Tuesday next week, so Tuesday, March 3rd. There has been a change on the assignment. Specifically, I noted that a problem that I had meant to assign was not actually the number that I had typed. So if you've tried to do problem 2.9 and been a little confused because we haven't covered it yet, well, that's because we're not covering it. So do 2.10 instead. I've also added our Markdown template for those of you who like to work in our Markdown and use those. Before we jump into the next part of matrix algebra, I want to let you guys know about a bit of a historical moment that's coming up in the statistics and machine learning environment. So this is the actual release statement that was published when our version 1.0.0 was first released. The 5th anniversary of that is Saturday, which means that R is now 20 years old. So officially, R turns 20 this weekend.
Still can't drink.
Still can't drink.
Yeah.
Might start kindergarten depending on how you count. Questions about the homework or anything from last time before we get started?
Oh, yeah, the 29th. Ah, yeah.
God.
I was like 5.
Going once, going twice. All right. So let's go ahead and do some more matrix rules. So today we'll talk about matrix decompositions and essentially how you factor matrices. Toward the end, just like last time, we'll have some practice exercises for you guys to try. Some of those will require computation, so that's why I've asked you to bring your laptops. So this idea of matrix decomposition is analogous to factoring in scalar world. So essentially, how can I find components that when multiplied together produce some matrix of interest? So for example, given A, how can I factor or decompose that into B times C? Now there are a couple techniques that we'll talk about today. So for symmetric positive definite matrices, we have a really straightforward technique known as the Cholesky decomposition that we can use. Advantage of this is that it produces square root-ish transformations. So if we wanted to think about what a square might look like for our matrix, the Cholesky decomposition can help us out there. Again, this only works in a very specific situation. So for symmetric positive definite matrices, so that means square matrices as well. So if we're outside of that realm, what can we do? Matrix diagonalization is one option. Singular value decomposition is another option. So we'll talk about how these three approaches differ and where you might use them today. There are two properties of a matrix, the determinant and the trace, that are really important for figuring out what these three decompositions are trying to do. So we'll start by defining the determinant and defining the trace of a matrix. And again, none of this should ever be done by hand, ever. I will show some simple small matrices in the notes with some R computation just so you can see what everything looks like. All right, so let's start with the determinant of a matrix. The determinant is a mapping that takes a matrix and maps it onto, say, a real number. So the determinant is denoted with DET or vertical bars. So bar A bar also denotes the determinant. I prefer the DET notation purely because that's also the function that we'll use to calculate the determinant of a matrix. For small matrices, we have nice closed form representations of these things. So for example, for a 2 by 2 matrix, the determinant is found by taking the product of the diagonal elements A11 times A22 minus the product of the off diagonals A21 times A12. For a 3 by 3 matrix, we have something similar. We're adding and subtracting products along diagonals. So we add the main diagonal product of the main diagonal. This second term here, A21, A32, A13, represents this second, or this first off diagonal, and then the second, and so on and so on. So we add and subtract products. You can kind of picture that there might be a nice expansion of this, and there is. It's the Laplace expansion. Again, this isn't really something that is going to be worthwhile when we're working with matrices of data to calculate by hand. So let's say that we have a 10 by 10 matrix below. Thinking about that pattern, we would have to find the product of the 10 elements on the diagonal plus product of an off diagonal here and here, off diagonal here and here. Then we'd start subtracting things. So instead, we'll use this function that's built into R called DET for determinant. The determinant of this matrix is negative 841,860. So again, this is just a function that takes the matrix, does a little bit of computation with it, and maps it onto a single value. So this determinant has some nice properties, or can give us some nice properties of a matrix. The first is one that we kind of intuited on Tuesday. For any square matrix, so any matrix with dimensions r by r, A is invertible or has an inverse if and only if the determinant is non-zero. So non-zero determinants imply that the inverse exists, and the inverse existing implies that the determinant is non-zero. This is a two-way implication. So does A have an inverse? Well, we've calculated the determinant. We know that the determinant of A, even though it's negative, it's okay that it's negative. We only need it to be non-zero. So yes, this matrix A should have an inverse. We can find the inverse of matrix A using the function in R called solve. So solving a matrix in R just returns the inverse should it exist. So this is the inverse of matrix A. We might like to verify that this is in fact the inverse, so I can use that percent asterisk percent to do matrix multiplication. If I take the solution or the inverse to A times A, I should expect to see an identity matrix here. So I should expect to see ones on the diagonals, zeros on the off diagonals. We're not perfectly there looking at this. We have a lot of numbers times 10 to the negative 16th, 10 to the negative 17th. This is purely a function of how computers do this calculation. It's the identity matrix. So you'll see that happen quite often when you go to do a calculation or verify some result. You may see decimals, but if they're decimals to the 16th or 17th decimal point, we don't really worry about those. Questions so far? What are some properties of determinants? Well, we can effectively factor the determinant. So if we want to find the determinant of a matrix A times B, well, we could just take the determinant of matrix A times the determinant of matrix B. And this expands, so we can multiply for 3 matrices, 4 matrices, and so on. Second property, determinants are invariant to transposition. So that means that the determinant of A transpose is the same as the determinant of A. So it doesn't matter if we transpose the matrix. If A is invertible, then the determinant of A inverse is 1 over the determinant of A. So for our problem, without calculating it, we know that the determinant of that 10 by 10 matrix is going to be 1 over negative 841,060. Similar matrices have the same determinant. So if a matrix is similar to some other matrix, their determinant will be the same. If we reorder, so if we swap rows or columns in the matrix, we change the sign of the determinant, so we may flip it from positive to negative. Adding multiples of rows and columns to one another does not change the determinant. And then finally, multiplication of a column or a row with some scalar lambda scales the determinant. So for example, if I take all of the elements in my matrix A, multiply them by some scalar lambda, the determinant is then raised to the n power because we have those n rows or n columns in this matrix. So these are some useful properties of determinants. I'll pause here for a minute so that you can catch up writing. Again, PDFs of these slides will go up after class.
For the first one, I know we talked about how it matters if you like multiply A times B or B times A.
Mm-hmm.
When you're doing the determinant of AB, is there anything we have to like consider there? Because I know you can break it out and determinant A times determinant B.
Mm-hmm.
But would that be the same as determinant BA?
So determinant of A times B should be the same as the determinant of B times A. The reason why order matters with matrix multiplication is that if the dimensions aren't conformable in both directions, you might not be able to do that operation. Here we're thinking of determinants as being properties of square matrices, so order doesn't matter. Other questions? So here's some theorems or some results that we can use with determinants. So theorem 1, a square matrix has determinant non-zero if and only if it is of full rank. So the rank of the matrix is n. Now remember that rank of the matrix represents the number of independent rows or columns. So in order for that determinant to be non-zero, all of our rows or columns have to be linearly independent. We cannot get one column of the matrix by adding two others together. So what this means is that if we want to find an inverse of a square matrix, it has to be full rank. Because full rank implies determinant non-zero. Determinant non-zero means that we have an inverse. So all of these properties are connected. So in order to know whether or not that solution to a matrix will exist or know that the determinant is non-zero, we can simply find the rank of the matrix. Or we can find any of these to verify the others. So the next useful property or function related to a matrix is something called the trace of the matrix. So for a square matrix, the trace is defined as the sum of the diagonal elements in the matrix. So the trace just takes everything on the diagonal, adds it up, ignores the off diagonal entries. Those do not enter the trace in any way. So the trace is just defined as the sum of the diagonal elements. There are some nice properties of the trace. So the trace of two matrices added, so the trace of A plus B, is equal to the trace of A plus the trace of B. Why? Well, when we're adding matrices together, we do that element-wise. We add together the elements in the matrices, so we're just adding those off diagonals together. The trace of a matrix multiplied by a constant alpha is just alpha times the trace, because again, we're just adding the diagonals. The trace of the identity matrix. So this identity matrix has ones on the diagonal, zeros everywhere else. So the trace of the n by n identity matrix should just be n. And then finally, the trace is invariant to multiplication order. So the trace of A times B is the same as the trace of B times A. Questions so far? Again, this isn't intended to be a deep dive into these. It's more of a, here are terms that you will see later. So the next major set of terms that you'll see later related to properties of a matrix are the eigenvalues and the eigenvectors of a matrix. So we're going to let A, again, this n by n should be up in the subscript. So A is a square matrix. Lambda in and R, so these real numbers, lambdas, are eigenvalues of A. And X is the corresponding eigenvector if this is true. So if I can take our matrix A times some vector X and get a scalar times that vector X, then lambda is an eigenvalue, X is an eigenvector. So a couple properties that follow from this. So the rank of some matrix A minus the eigenvalue times the identity will be less than n. And the determinant of A minus the eigenvalue times the identity is less than 0. Where eigenvalues come into play for us a little bit later is when we're looking at things like matrix rotations. How do we take a matrix, produce some function of it with linearly independent vectors? We'll do that based on the eigenvalues. Jake?
Sorry, is that the rank of the difference in the first property?
Yes, it is.
Okay.
That is just a premature close parentheses. All right, so to get these eigenvalues and eigenvectors, we've got a function built into R called eigen that produces both of them. So I can take my 10 by 10 matrix A, calculate the eigenvectors. Here I'm just sticking them into some object Y. Y contains two elements, or two objects. It contains the values and the vectors. I can call the eigenvalues. Now here, notice I've done something a little different, a little interesting. This is an incomplete specification, so instead of writing the full word values, I've written VAL. R will look through that list of objects in any data frame or in any R object, try to find ones where it matches. So VAL is enough to call values. VA would be enough to call values. V would not, because there's values and vectors. So here are the eigenvalues. What's one thing that you notice about these? They're complex numbers. That's okay. We also have eigenvectors, complex numbers. How many eigenvalues are there for this matrix? And 10 by 10 matrix, we've got 10 eigenvalues. We should have the same number of eigenvalues as rows and columns in the matrix. However, they may not necessarily be unique.
These are only applicable for square matrices.
Mm-hmm.
So is there like a set number for eigenvectors?
Yes, there should be n eigenvectors too.
Okay.
Again, may not be unique. So properties of these eigenvalues and eigenvectors. Matrix and its transpose, so A and A transpose, will possess the same eigenvalues. They may not have the same eigenvectors. Those could be different. Matrices that are similar possess the same eigenvalues. And symmetric positive definite matrices always have positive real valued eigenvalues. So again, that's another really attractive property of working with symmetric positive definite matrices if we can, because those eigenvalues will be positive and real valued. The word eigen here comes from German referring to own. So these are the property or the own properties, or this matrice's own properties. That's where this term comes from.
It's not some dude's name.
It is not someone's name. Usually things are someone's name. So that's fun. So based on the eigenvalues of A, what can we infer about the properties of A? Well, looking at these eigenvalues, they're complex, so A probably is not symmetric, positive, definite. None of them are repeated, so A may be a full rank. In fact, we can check to see whether or not A is positive, definite, and it is not. So let's consider a simple symmetric matrix B. So here's one that has 3 on the diagonals, 2 on the off diagonals. Very boring matrix. Eigenvalues are 7, 1, and 1, so these eigenvalues are not necessarily distinct. This matrix is positive definite. Anyone remember what positive definite means?
Stuff down.
Something's greater than 0.
Take a stab and say the determinant.
It's not the determinant. Yeah.
So if you have a symmetric matrix A, such that for all x in matrix B there exists x transpose of A x equal to 0.
Yeah. So positive definite matrices are such that we can take a vector, x transpose A times x. That should be positive. We can also have strictly positive definite where that is strictly greater than 0. So this is a positive definite matrix. We also know that this is a symmetric matrix just by looking at it because all of the off diagonal elements are mirrored along the diagonal. Questions?
Can we perform matrix operations on things like tables, or does it have to have that as matrix?
It depends on the function. So the question was, can we perform matrix operations on things that are classified as tables in R, so as tidyverse data frames? It depends on the function. So some of the base R functions will be looking for that matrix class. So you may have to reclassify your tibble or your data frame as a matrix for some of this to work. Other functions that are not necessarily base R and have maybe been written by other tidyverse friendly developers could take that tibble. Josh.
So I'm gonna ask the question.
Yeah.
Is it as simple as a matrix call to recast a tibble or a data frame as a matrix?
Exactly, yes. So I could, for example, open R.
Because I can imagine us casting it as a matrix, doing some stuff to it, and then recasting it back to a tibble.
I suspect figures though. I mean matrices have to have numbers, probably all have to have the same type of numbers. If you have 1 to 10 sort of factors, so that might won't fail us.
Yeah.
Well, there are ways to reclassify those factors. That's why things like dummy variables are so useful. So dummy variables take on zeros and ones for each level of a categorical factor. That's how we incorporate categorical variables into these matrices. So here's the MT-CARS data set, for example. We'll look at the first few observations.
That's got to be similar to how multiple linear regression is solving for categorical variables. It's just coercing them to some kind of numerical value and operating on it.
It absolutely is.
Yeah.
So we can use a function if we're working in R called as.matrix that will reclass this as a matrix. So MT-CARS, you notice that R is recognizing it as a data frame, telling you how many observations out of how many variables. A is now just numerical with 1 through 32 rows, 11 columns.
And you will not lose row and column names when you go back and forth. won't
You
do that
should
anymore.
not lose row and column names. So let's test that just to be sure. So let's class B. Hello, tidyverse.
Sorry.
No, it's fine. Tangents are fun. Let's try reclassing this as a tibble. As.tibble is deprecated. We'll use as underscore tibble instead. So B has 32 observations of 11 variables. We kept all of the column names. We did lose the row names.
Progressive nevertheless. Make that a lot more easy than I would have thought it would be.
But knowing that, you can just store the row names
Absolutely.
and then stick them on there at the end.
Yep. Or you could do something like set the row names of B to be the same as the row names for empty cars. Setting row names on a tibble is deprecated, but it'll let me do it anyway.
Damn deprecation.
Darn deprecation.
Always a pain.
Someone tweet Hadley about it.
I will.
Questions?
Have you ever, has there ever been a time where you've actually needed to use any of those matrix operators on something like a tibble?
Yes, so there have been cases where I've needed to do that. So, for example, if I were writing my own analysis, so instead of doing least squares or some sort of spatial Kriging model, for example, in my research, if I needed to write my own, then I may need to reclassify things.
Okay.
Other questions? Josh, I'm glad you brought this up because it may be useful on the homework.
Oh, second.
Okay. So some other connections between determinants, traces, and eigenvalues. So first, the determinant of a matrix is just the product of the eigenvalues. So if you have those eigenvalues, just multiply them together, you get the determinant. Certainly can be a much more efficient way to calculate the determinant if you have the eigenvalues. So for example, just to confirm this result for A and B, I can calculate the determinant. I could also use prod to get the product of the eigenvalues. Here I'm just applying this eigenvalue function directly, get the same result. So that's lovely that that works. Here's the other technique or the other property that's useful for us. If we want to get the trace of a matrix, so the sum of the diagonal elements, it's the same as the sum of the eigenvalues. So again, if we've got the eigenvalues of a matrix, we can do a lot of things quickly. Jake?
How often, now that I'm thinking about Josh's question and I'm talking about all of these things, we're talking about square matrices, so how often will something like that actually be useful converting a data set to a matrix and then back to a data set? Because if it's not square, you can't really do a lot of this cool stuff.
So where this comes into play as very useful in statistical practice is working with variance and covariance matrices. So those have the variance of variables on the diagonals, the covariance between variable 1, variable 2, and so on the off diagonals. Those are square. Another example where you run into square matrices, distance matrices. So the distance between 2 points, you can represent that as a square matrix, 0.1, 0.2, so on.
I wonder how useful this is for like just any generic adjacency matrix.
Very useful.
I mean, you can also approximate a lot of these things on non-square. Just get hairy.
There are non-square analogs. There are also decomposition techniques to compose non-square matrices based on square matrices. That gets really nice too.
I'm guessing they don't consist of add a bunch of zeros to get a square matrix.
No, but that can work. It's just not full rank, which is the problem. All right, so again, confirming this result, sum the eigenvalues does in fact result in the trace. So, theorem, the eigenvectors of a matrix with n distinct eigenvalues are linearly independent. So if our matrix A has n eigenvalues, they're all unique, so none of those eigenvalues are repeated, the eigenvectors are independent. The eigenvectors will be unrelated. If we have a square matrix that has fewer than n linearly independent eigenvectors, or with fewer than n distinct eigenvalues, we call this defective. So these matrices are defective. Their eigenvalues are repeating, their eigenvectors are not independent. Going back to our examples A and B, B is a defective matrix. B is defective because two of its eigenvalues repeat. The first eigenvalue is 7, the second is 1, the third is 1. So, here's where the limitations of square matrices sort of come into play. Because all of this applies in the square matrix space, but what if we don't have the square matrix? Well, we can get them. So if we have some matrix A with dimensions m by n, so A is not required to be square, we can always get a symmetric positive definite matrix by doing the following. Just take A transpose times A. That's symmetric, that's positive definite, if the rank is n. If it's not, then it won't be positive definite. So that's how we get around this problem. Even if A isn't square, A transpose A will be. So for example, one situation that we've seen where we've used this sort of technique from last time is the Moore-Penrose inverse. A prime A inverse, or sorry, A transpose A inverse. A may not be square, but that will be. So for our matrix A, let's build an S and see if this holds. So A was not positive definite. A is a full rank, however. A is a 10 by 10 matrix. Its rank is 10, so that's the highest it can be. If I create a new matrix S, which is A transpose times A, that is positive definite. Jake?
A matrix can only be full rank if n is less than or equal to m, right?
No. So we can have full rank matrices of either rank M or N. The matrix has to be equal, or the rank of the matrix has to be equal to the minimum of M or N. For non-square matrices.
It's equal to, not like equal to or greater than.
Equal to. Yep, that's the biggest the rank can possibly be.
Oh, okay.
So this sort of leads into a theorem called the spectral theorem. And what the spectral theorem says is this. So if A is a square matrix and a symmetric square matrix, then there exists what's called an orthonormal basis of the corresponding vector space consisting of eigenvectors of A, and each eigenvalue is real. What the spectral theorem means in plain English is that if A is a square symmetric matrix, you can decompose it using the eigenvectors and the eigenvalues. In other words, you can come up with some set of matrices that when multiplied together will produce A, and that set of matrices will depend on the eigenvectors and the eigenvalues. Further, all of the eigenvalues will be real numbers. Let me go back because I think I hear a lot of people still typing. Then we'll talk about how we actually use this thing. Good to go? Okay, so here's how we use the spectral theorem. So the spectral theorem, again, tells me that I can take a square matrix and decompose it based on the eigenvalues and the eigenvectors. So what we end up doing is creating what's called a PDP decomposition, or an eigen decomposition. So the eigen decomposition of a symmetric matrix exists and looks like this. So D is a diagonal matrix, so it only has entries on the diagonals. The columns of P contain the eigenvectors. So we've got a matrix of the eigenvectors times a diagonal matrix times the eigenvectors transposed. That produces A. So if we've got those eigenvalues, got those eigenvectors, we can produce this decomposition just based on those values, which is pretty cool. Another way to factor matrices is something called the Cholesky decomposition. So what the Cholesky decomposition essentially does is create not exactly square roots of a matrix, but as close as you can get to the square root of a matrix. So the Cholesky decomposition says that, again, a symmetric positive definite matrix can be factored into a product L times L transpose. L is a lower triagonal matrix. So that means that L has values on the diagonal and values on the lower triangle on the matrix. Everything above the diagonal is 0. L transpose is in an upper triagonal matrix. L transpose has the same diagonal values as values up here on the upper half, so above the diagonal, zeros everywhere else. So we can factor or square these things. If we're working with something like a variance-covariance matrix, where we have variances on the diagonals, a lot of times in statistical practice, we want the standard deviation instead, the square root of the variance. So this Cholesky decomposition might help us get to square roots of the variances. So the symmetric positive definite matrix property keeps coming up because in order to do these compositions, or these decompositions, we want that symmetric positive definite property. If it's not symmetric or positive definite, we cannot do this. So, for example, this is what one of those variance-covariance matrices looks like. So this is the variance-covariance matrix for 3 input variables, x1, x2, x3. So the diagonal elements represent the variances. So we've got the variance of variable 1, variance of variable 2, variance of variable 3. On the off diagonals, we have the covariances. So these are similar to correlation, except they're not squared. They're not bounded between 0 and 1, or -1 and +1. So this covariance between x1 and x2 tells us how x1 and x2 vary together. Covariance between x1 and x3 tells us how x1 and x3 vary together. Covariance between x1 and x2 tells us how x2 and x3 vary together. What's one assumption that we often make when we are building a statistical model or a machine learning model? Josh?
That the variability is normally distributed.
Yes, we do assume that the errors are normally distributed.
Error independence.
Error independence. So we also, if we can, assume that the x1s, x2s, x3s are independent. That assumption turns this variance-covariance matrix into just a simple diagonal matrix with zeros everywhere else. So once we start having variances or covariances, related variables, these matrices get much more difficult to work with.
So when you say that assumption turns that into just a diagonal matrix, is that because we are essentially saying, we are assuming that there is no covariance here, we're going to set it to 0, and now we have a diagonal matrix?
Yes, so if we assume that variables are unrelated, their covariance is 0, becomes a diagonal matrix. So lots of really fun simplifying assumptions. Okay. Talked about the diagonals, talked about the off diagonals. Why should this matrix always be symmetric? Yeah.
Because, so like, I'll just take an example. Like the covariance of x1 and x2, it's in first row, second column, and second row, first column. So it should always, that covariance shouldn't change.
Yeah.
Between variables.
So that covariance or that relationship between x1 and x2 shouldn't change here compared to here. Should be the same. So we'll end up with a symmetric matrix. So for a general 3x3 matrix, and if you haven't noticed yet, this gives it away. I got to the point where I was just taking screenshots from the book. So this is another screenshot from the book of this Cholesky factorization. So here's how this might come together, how this might work for a 3x3 variance covariance matrix. So A is our variance covariance matrix. We'll factor it or decompose it like this, just generic L1s, L2s, and so on that meet this structure. So this first element, this would correspond to our variance between, or our variance of variable 1. For us, this corresponds to the variance between variable, or the variance of variable 2. It's not exactly the same as what a square root of that variance would be when you build out the Cholesky decomposition, but it's easy enough once you've created this to solve for those square roots of the individual variances, so to solve for the standard deviations. But so that this doesn't become a misconception, those diagonal elements of the Cholesky decomposition will not exactly be things like standard deviations.
It gives us something very close that we can then do some easy operations on and get what we need from it.
Exactly. Gives us something very close that we can use to get standard deviations.
And more specifically, something that is very well defined to be
Yes.
like a certain thing away from what we need.
Yep, exactly. Jake, you had a question?
Are there limitations on the types of different variables that can be used to create this matrix? Do they have to be real? Do they have to be obviously numerical? Anything like that?
So actually, no, they don't have to be numerical. We can use categorical variables as long as we create those dummy variables. So again, we replace levels of factors with 1s and 0s. Then we can do these sorts of operations. Technically, trying to think, they should have to be real because I believe complex numbers won't satisfy that positive definite requirement. In practice, if we're thinking about measurements or variables, very rarely do we go out and collect data in the complex plane. Other questions? It could be done in physics.
Yeah.
Okay, so some uses for this Cholesky decomposition. This is often used to generate simulated data from multivariate distributions. So for example, if you want to simulate data from two, say, normal distributions that are correlated, we'll use this decomposition to help us out, to help model that. Or if you're simulating something like spatially correlated data. So if you're simulating data that varies according to row and column or coordinate locations, something like this is happening in the background to help conduct that help build that simulation. Creating linear transformations of random variables. So for example, in linear discriminant analysis, we build linear combinations of the underlying variables that explain a certain amount of variability. We can do this via these decompositions. And then finally, you can actually use this Cholesky decomposition to compute determinants a little bit quicker. And I'll leave that to you guys to maybe conceptualize why that's the case. To find the Cholesky decomposition for matrices in R, you use the CHOL, or the CHOL function. Again, we need square matrices, we need positive definite matrices, so even though A is square, it is not positive definite, so we should expect to see an error returned. Matrix B is square and positive definite, so we get back the decomposition. We'll only get back the decomposition in one direction, so this will return the upper triangular matrix. To get the lower triangular matrix, just take the transpose. So we only need to retain and store one. So next technique or next tool that's useful for us is something called matrix diagonalization. So a diagonal matrix, again, has all off-diagonal matrices equal to 0. These are really awesome if we can get them. They're easy to store, they're easy to compute with. They also have some great properties. So the determinant of a diagonal matrix is just the product of the diagonal entries. What does that maybe suggest to you about the eigenvalues of a diagonal matrix?
They lie along the diagonals.
Eigenvalues lie along the diagonals, another really attractive property. We can raise matrices to a power if they're diagonal matrices just by raising the elements of that power, or the diagonal elements to a power. So if, for example, we assume that the covariances or the off diagonals are all 0, well, then we could find the standard deviations just by square rooting all the diagonal elements, which is pretty great. The inverse is the reciprocal of the diagonal elements, assuming all of them are non-zero. So also pretty great from a calculation and modeling perspective. A matrix A is called diagonalizable if it's similar to a diagonal matrix. That is, there exists an invertible matrix P such that D is equal to P inverse A times P. Now, this is similar notationally to our eigen decomposition. So we wrote our eigen decomposition of a matrix as PD P inverse. We right multiply both sides by P. We left multiply both sides by P inverse. There we get the diagonalizable form of the matrix. So based on that eigen decomposition, the diagonal values on D should be the eigenvalues. The columns of P should be the eigenvectors. Yeah?
So I'm going to ask a question that probably should have been obvious last lecture.
Feel free.
When you said right and left multiply, I'm thinking that implies that it is very specific that you multiply everything on the right and the left-hand side, which equals, equations on the correct side.
Yes. So when you're working with matrices, the side that you multiply on matters. That's because of the dimensions of the matrix.
Okay. Sorry.
No, that's fine. That's a good question. Other questions? Mark?
Will R always executed in the same order, presumably, in terms of right versus left multiplication? Like, is it going to start from the left and keep moving?
Yes. So So in fact, this does bring us back to the eigen decomposition. So the eigen decomposition gives us a way to diagonalize a vector. We can use diagonalization to get back to the original vector, or the original matrix A, if we have the eigenvalues and the eigenvectors. So we can get from one to the other. This can only be done for non-defective matrices. So defective matrices are ones where the eigenvalues are repeating. So if eigenvalues repeat, we cannot do this. If the eigenvalues are all unique, we can. The columns of P are the eigenvectors of A. So kind of visually, here's what ends up happening. We take a matrix, we scale it, we rotate it, and then we can undo this operation to go back. Something where in maybe data science, you've seen this before, is when we do principal components. With principal components, we take correlated inputs, so inputs that maybe form an ellipse when we plot them. We rotate them to linear combinations of the input variables. So we use the eigenvalues and eigenvectors to get there. Theorem, a symmetric matrix can always be diagonalized. Okay, so procedure, we can do this by hand. Better procedure, just do this in software. Here's some results related to this. So if A has an eigenvalue decomposition, then we can do the following. We can raise a matrix A to some power, K, by taking this eigen decomposition. P and P inverse do not change. We just simply raise the diagonal elements to the power K. The determinant, just based on the fact that determinants are multiplicative inside, the determinant of A is the determinant of P times the determinant of D times the determinant of P inverse. Now let's say that A is not a square matrix. It would still be really useful for us if we could decompose it. So if we could figure out some subcomponents that when multiplied together create A. We do this using what's called the singular value decomposition technique. So for singular value decomposition, we'll let A be a rectangular matrix of rank, can actually be of less than full rank. It can have rank 0, so they're all, none of them are independent. Rank up to minimum of n times n. The SVD is a composition that looks like this. We'll take A and factor it into a square matrix that's m by m times an m by n matrix in the middle times an n by n V matrix. So we'll take A and break it into the product of a square matrix times a rectangular matrix times a square matrix. Further, this matrix in the middle, the sigma, all of the diagonal elements should be greater than or equal to 0. All of the off-diagonal elements will be 0. So we'll have a square matrix times a diagonal matrix that's perhaps augmented, some extra rows or columns of zeros, times a square matrix. We like square matrices, we like diagonal matrices. So this is how we make that matrix A a little bit easier to work with. The diagonal elements of sigma are called the singular values. The elements of U, so U is this square matrix here. Elements of U are the left singular values. Elements of V are the right singular values. So singular values come from that middle matrix sigma. Left singular come from the left matrix. Right singular come from the right matrix. This sigma matrix in the middle has a few nice properties. Sigma is unique, and sigma has the same dimensions as our starter matrix A. So if M is greater than N, for example, the matrix has diagonal structure up to row N. We call the elements or the singular values lowercase sigma. Then we just add a bunch of rows of zeros at the bottom. For a column matrix, same structure, we're just adding a bunch of columns at the end to create that matrix sigma. The singular value decomposition does something very similar to the eigen decomposition, rotates the matrices. However, it's now doing that in terms of non-square matrices. And further, there's something nice about the singular value decomposition. It exists for any matrix. Not necessarily square, not necessarily positive definite, not necessarily symmetric, much more general decomposition. To find the singular value decomposition of matrices in R, you'll use a function called SVD. There are diagonal elements, so these are the diagonal elements of sigma. So these are going to go in that middle matrix, zeros everywhere else. The U matrix is square, otherwise doesn't really have many nice properties. The V matrix, square, doesn't really have any nice properties. For B, here's the singular value decomposition. Have we seen numbers like these before for this B matrix? What were the eigenvalues of B? 7, 1, 1. The eigenvectors are here. So for square matrices, singular value decomposition is the eigen decomposition. And there are details in the textbook if you want to know how this all works out. So, some theorems or some results. First, the singular value decomposition exists for any matrix. The eigen decomposition only exists for square matrices. Second, vectors in the eigen decomposition are not necessarily orthogonal. Vectors in the singular value decomposition are orthonormal, so they're linearly independent, represent bases. These are essentially rotations of the matrix. Diagonal elements in the singular value decomposition are all real and non-negative. For symmetric matrices, the eigen decomposition and singular value decomposition are the same. U and V are not usually inverses. So if I take U times V, I don't get the identity matrix. In fact, most of the time, I shouldn't even be able to multiply U times V in singular value decomposition. Why?
If your input matrix isn't square, you're not going to have the same information.
Yeah, if your input matrix isn't square, U and V are going to be square matrices, but with different dimensions. So we shouldn't be able to multiply them in most cases. So we've got about 15 minutes left. I want to show you one application of where we might want to use a decomposition technique, and that's with matrix approximation. So we can approximate a matrix with a lower rank matrix, so a matrix that is simpler using this singular value decomposition. So for example, I can create a matrix with rank 1 by taking the first vector in the U matrix times the transpose of the first vector in the V matrix. What these rank 1 matrices essentially are are the same values all the way across the rows. They're just multiples of another. So for example, 1, 2, 1, 2, 4, 2 would be a very simple rank 1 matrix. We can then write a matrix of rank R, so we can take A, write it as the sum of these rank 1 matrices. So essentially we can take A, break it up into layers that come back together and build up the original matrix. If we choose not to go all the way up to the original rank of A, if we stop a little bit sooner, say K, we call that a rank K approximation. So this A hat will not be the same as our starter matrix A, but it should be a good approximation. Here's one area where we might use this in machine learning. We might use this with image processing. So what you're looking at here is an image of Stonehenge. I've taken this image, or we've taken this image, converted it to grayscale. So deepest, the truest black is stored as a 1, lightest white stored as a 0, everything else a decimal point, representing the darkness of the grayscale. So take this image, essentially treat this as a matrix of values between 0 and 1, and we can find those decompositions based on the singular values. So here's the first approximation. So this is built using the first column of the U matrix, the first column of the V matrix, and the first singular value, which happens to be 228,000, and so on. Doesn't really look like Stonehenge. This is using the second column of U, second singular value, second column of V. Still doesn't really look like Stonehenge. Third, fourth, and fifth. But if I take these, start adding them together. So this is the first one. This is the first one plus the second. First, second, third. If I add together those 5 images, looks a little bit more like Stonehenge. So this is what pictures using my digital camera in middle school look like. Here's the original image. We can kind of start to make out Stonehenge. If we add more and more layers, we should get closer to that original image. Why would we want to do this? Well, here's why. That original image was a 1432 pixel by 1910 pixel image. So that requires about 274,000 individual values to store.
That's 2 million.
2 million, thank you. That rank 5 decomposition though, we've got all of these rows and columns are essentially the same, multiples of each other. We've only got 5 of them. So that's the size of the approximated image. So we've taken this down to less than 1% of the original. These approximations are also a lot quicker, or a lot easier to look for patterns in. So if we can look for patterns in the layers of these, we can maybe start to build an image recognition system that's going to look for these sub-patterns rather than try to look for a pattern in the full, complete image. Yeah?
So I'm starting to think like edge detection type things.
Mm-hmm. Edge detection is absolutely a good application of this. So for example, looking at Stonehenge in these lower rank images, down here, the original picture doesn't really change much. Up here, the original picture doesn't really change much. So we can kind of tell just based on this low rank approximation that Stonehenge maybe starts about here, maybe cuts off or ends about here. Jake. Oh, sorry, Patrick.
So for that pattern recognition,
I'm so sorry.
no, so I guess my question is like, For that pattern recognition,
Mhm.
when you say that it's really good at picking up some patterns, would that translate to further back pictures? Because when I look at the first one, I'm thinking
Mhm.
people, and then
It eventually does, yeah. So
Okay.
after a while, notice these singular values get smaller. That's not by design, or that's not by accident, that is by design. Ugh. So as you keep adding more and more layers, you don't really get much additional information. Think of each of these like trying to capture the most variation in the image with a rank 1 matrix. So we're looking for sources of variation. So a pretty big source of variation here is the sky versus the grass. Now we're looking at vertical variation in the stones. Now we're looking at variation down here, and so on, and so on. So we're picking up those different layers of variability. Patrick. I'm blonde and I don't sleep much. Okay, so we'll skip spectral norm stuff. I'll show you this Eckert-Young theorem. You don't really need to know much about it except for this. There is a theorem that tells us how much error we can introduce by approximating A by a rank K approximation. Furthermore, we can place an upper bound on the error so we can figure out, well, what's the maximum error we're going to introduce in our image by doing this. So that's all this theorem really gives us. Yeah?
Is there a very fortunate relationship between the amount of error or information that you lose, I'm assuming, and how much compression you get? So like, do you get like, 90% of the information with like 10% of the size, or is it more?
It varies. It varies from application to application, but generally you get more information from the lower ranks than adding additional high ranks. So there's diminishing of returns, essentially,
Okay.
by adding more complexity to this.
So it starts to converge to like not giving you much more.
Yep. So the last thing I want to talk about briefly is expectation and variance. So expectation of a random variable, so just any random variable, single valued x, we call E of x or mu the expected value. So essentially this is the long run mean of the variable, what we would expect to see over repeated random trials. For a discrete random variable x, we find this by summing up all of the possible outcomes little x times the probabilities. For continuous x, we find this by integrating all of the possible x's times their density function, little f of x. The variance of the random variable x measures how varied the variable is. So the variance is defined as the expected value of the quantity x minus the mean squared, which with a little bit of algebra simplifies to this, the expected value of x squared minus the expected value of x quantity squared. Standard deviation, which you probably use in intro stats or intro business stats, is the square root of the variance. So just like individual random variables have expected values and variances, what if we had a matrix that was filled with random variables? Those matrices filled with random variables have expected values and variances. So think about maybe collecting data. We record or we model data as being a set of random variables in a matrix with expected value and variance. Most of the sort of math stats properties of expected values and variances still hold with matrices, but with a little tweaks, just because we're moving into that multidimensional space. So for capital X being a matrix of random variables, little x being a vector of random variables, we've got a couple properties. A, B, and C are essentially constant matrices, so they're not assumed to be random. We can factor out expected values. Constants that we add to the expected value, they don't add any variability, so we get expected value of A x B plus C is A times E of x times B plus C. Still left-right multiplication matters here too. Variance of a vector is whatever this A matrix is times the variance of the vector times A transpose. There's some other expected values of these vectors. I'll go back. So expected value of ax plus b, for example, is a times the mean vector. So m is the vector of the means of the expected value, or the means of the x's, plus b. Expected value of a times x is am. Expected value of e plus b is m plus b. All of that kind of combines to create this first property. Now notice, so remember, we think of matrices or as vectors as really just n by 1 matrices. So all of these properties should hold for matrices as well, assuming the multiplication dimensions work out. The very last thing I want to talk about today, and unfortunately we won't get to the practice problems, but I will post them with solutions in the PDF, is something called a quadratic form. So assume that A is a symmetric matrix, M is the expected value of some vector x, and sigma is the variance of some vector x. Further, we'll assume that all of the x's are independent. So a quadratic form is something like this. X transpose times A times x. Where did we see quadratic forms? More Penrose has them. We're thinking about positive definite matrices as being defined in terms of these quadratic forms. X transpose times A times x. There are expected values of quadratic forms that depend on things like the trace. There are expected values of a whole bunch of others. Again, I'm putting this on blue line, so don't feel like you need to write this down. Here's the reason why I'm showing you this. You will likely see some of these applied again, especially in ISLR when we get to things like principal components, support vector machines. So do not be scared of all of these formulas. There will be a quick reference for all of these, but this is just simply how we find those expected values and those variances. Also further motivation for why the trace, which is just the sum of the diagonal elements, why that thing's so darn important. All right, so we will stop here because we're about out of time. There are 4 test yourself problems at the end of these notes. There are also some solutions to work you through how to solve all of these, so these will just be extra practice problems. Next week, we will come away from the math of machine learning a little bit. We'll talk about regression splines, polynomial regression. After spring break, we'll switch over to unsupervised. So that's where we're headed next. Have a great weekend, and I'll see you guys on Tuesday.